Right, I'd like to thank the organizers for inviting me. And I should say that this is joint work with Anton Bernstein, who's in the audience, and Anush Sarian, who are both at the University of Illinois, Urbana-Champaign. So today I'm going to be talking about container type results in algebraic geometry. So we're really motivated by the very recent hypergraph container results, especially the applications in number theory, and we wondered what we could say in algebraic geometry. So actually looking directly at the varieties of certain types, the properties, actually, it made more sense to prove things directly in algebraic geometry, and the technical conditions are a little bit simpler there as well. So I'd like to motivate this by talking a little bit about hypergraph containers. I know a lot of you are familiar with graph containers or hypergraph containers, but I'd like to run through some motivation. So a number of objects from different areas can be encoded as the independent sets and certain uniform hypergraphs. So a k-uniform hypergraph, our hyperedges all have exactly k elements, and an independent set is just a subset of the vertex set that doesn't span any of the edges. So for example, one of the most classical objects in extremal combinatorics is looking at the k-uniform intersecting families on ground set 1 through n. So here we're taking k-element subsets, and we want all of them to pairwise intersect. And so, for instance, we can encode these as independent sets in the appropriately chosen Kneser graph. So here we have n is equal to 5 and k is equal to 2, and here 4, 5, 2, 5, and 1, 5 are an intersecting family. So in Matroid theory, Whittle introduced this on Monday, the sparse paving matroids. So both the matroid and its dual are paving, can be thought of as in one-to-one correspondence of independent sets in the appropriately chosen Johnson graph. So here the Johnson graph, we're taking all our element subsets, and we put an edge if and only if the intersection is exactly r minus 1. So the non-bases actually are independent sets in the appropriate Johnson graph. So, and in particular, we were inspired by a number of results in number theory. So for instance, an interesting object to study are k-term arithmetic progression-free subsets of 1 through n. So we could think of the hypergraph where the vertices are 1 through n, and for our edges, we just throw in all k-term arithmetic progressions. So we can think about sort of the classical result of Simoretti in this language. So basically, he's saying that the largest Ka-free subset of n has size at most little o of n. So we can think about looking at the size of the independent sets in this hypergraph. So in order to enumerate these objects, which is often a question that we would like to study, it comes down to counting the independent sets in the auxiliary hypergraphs. So we have a couple of trivial bounds. So here alpha of h is the independence number, so that's the size of a largest independent set. So we could fix one of the largest and take all possible subsets because each of those will also be independent. So we have at least to the alpha of h. And likewise, we have a trivial upper bound. So here, a candidate to be an independent set, you have to be between size 0. Yes, we count the empty subset as an independent set. So you have to be between 0 and alpha of h, so we just take all possible candidates. So of course, these bounds could be quite far apart, but really what in essence hypergraph containers is telling us is that the lower bound for certain auxiliary hypergraphs that we care about is really sort of the correct order of magnitude. So we can't say this, of course, in general for all hypergraphs, but it's kind of amazing that a lot of the ones that we care about, we can upper bound the independence number. And in general, that's an ongoing question in general. So for instance, we were able to show that the number of intersecting k-uniform families on 1 through n is 2 to the 1 plus little o 1 alpha of the corresponding Kneser graph. So that's just an application of graph containers on the Kneser graph. Likewise, so one of the big conjectures in the field is that the number of sparse paving matroids over the number of matroids should tend to 1 as n goes to infinity. And using a modified version of graph containers, we get the log version. All right, so I wanted to mention this really beautiful theorem. So this appears in Balagh-Morris-Simoti, but it was first proved in earlier papers. So we have this concept of being delta k Summeretti. If we take subsets of at least delta proportion of the elements, and if we have a KAP. So they show this statement that for every density, so this is sort of a sparse version of the traditional Summeretti's theorem. So instead of delta is equal to 1, we could vary what delta looks like. So they show that for every delta and every k, we can find such a p where this works. So p is a function on n, where this works. So my notation here, this is a random subset, so you're picking the elements independently with probability p. So you're not meant to read this slide, so I wanted to include one formulation of graph containers and maybe talk about the graph case a little bit because it's simpler than the hypergraph case. So what you're really meant to get out of this slide, so here we're counting the number of independent sets in a graph of size exactly q plus r. And instead of upper bounding it by n choose q's plus r, we're upper bounding it by n choose q, where q is relatively small, times r choose r, where this r is also relatively small. So it's a better bound than n choose q plus r. So basically, if you have a graph that satisfies nice properties, which in this case means that it satisfies a local density condition, then we can prove this as an upper bound for the number of independent sets. So let's run through this and maybe talk a little bit about where the name containers comes from. So we need a definition before we get to the Scythe algorithm. So if we have a subset of the vertex set, we can do the following. So we can look at the subgraph of G induced by A and find the largest degree vertex. And then we can throw it out and repeat that procedure on the induced subgraph. So we get some sort of ordering, and so let's fix R and fix an independent set of size q plus r. And now we're going through a process where we're partitioning the vertices of our graph. So we're partitioning the vertex set into a set A, so that's available, a set S that's selected, and a set X, which is excluded. So for q times, we're going to find the max degree order. And then we're going to look at these vertices, so starting with V1, V2, V3, and so on, until we run across one that actually was in our independent set. So we want sort of the largest one, the biggest degree that is actually in our independent set. So we don't care about any of the previous ones. We're just going to throw those in the trash, put those into the excluded. But we will select this vertex. So we're only selecting things that live in our independent set at each step of the algorithm. And then anything that was a neighbor of VI will not be in our independent set, so we'll go ahead and put that in the trash as well. So let's make a couple of observations. So we did this q times, and each time we selected one thing. So the number of things we're selecting is q. And so this requires some proof, but what is left at the end as available is bounded. So according to our algorithm, the available vertices only depended on the things we selected, and the things we selected depended only on our independent set. So we never threw out anything in our independent set. We either selected it or it was left over in the available vertices. So we have the property that the selected things are contained in the independent set, and the independent set lives in A union S. So this is where the name containers comes from. We're going to talk about S being a fingerprint and A union S being a container. So in general, counting independent sets is hard. It's a hard problem, but if we could get a handle on where they live, it would be a much easier problem. So here what we're saying is if we can identify by this algorithm, this fingerprint, then we can track down where it lives, because we know it has to live in A union S, which is not going to be that much larger than the independent set itself, and it's going to be relatively sparse. So it has a lot of nice properties. So we end up bounding the number of independent sets of size exactly Q plus R by the number of possible fingerprints and the number of possible ways to extend it to a full independent set of size Q plus R. Okay, so that was for two uniform hypergraphs, right? So what can we say in general? So what happens when K is larger? So there's been a lot of work recently, and there's some very beautiful results by Balagh Semoti and Saxton Thomason independently. So I'm not gonna state the full hypergraph containers theorem, but I will mention that we need to be a bit more careful. So for the graph case, these local density conditions were enough, but for hypergraphs, we really care about how the edges are distributed. So we care about the maximum degrees, we care about the so-called co-degree conditions, so we care how many edges, so if you fix two vertices, how many edges they extend to, and your hypergraphs really need to actually have these very specific technical conditions. And so the proof in spirit is identical to Kleitman-Winston. It is a Scythe algorithm, but it's a much more complicated Scythe algorithm. So I'll explain a little bit here. So basically, you're starting with a K uniform hypergraph, and we're running the algorithm, but we're running the algorithm by constructing a series of partial fingerprints. So we're decrementing the uniformity and finding a fingerprint there, and then we decrement the uniformity and find a fingerprint there, and at the end of the day, we'll try to do this process again, maintaining a bunch of technical conditions, and we'll fail. And so then whatever is left, we'll call A, and that's going to be bounded. And we'll just take our fingerprint to be the union of these partial fingerprints that we were constructing along the way. So I'd like to say a couple of things about sort of the algebraic geometric setting. So if F is an algebraically closed field, then we say that a subset of F to the n is Zariski closed if it's the zero set of a family of polynomials. So furthermore, we're going to say that our Zariski closed set is irreducible if we can't split it apart, if we can't write it as the intersection of two non-empty proper Zariski closed subsets. And if it is actually a finite Boolean combination of these closed sets, we're going to call this constructible. So just a remark, we're irreducible if its closure is irreducible. So I wanted to maybe run through an example because we really were motivated by Semireti's theorem and the extensions of Semireti's theorem that were proven, especially in the Balagh-Semoti paper. And so let's consider this Zariski set. And so we could think of this as an algebraic hypergraph. So our vertex set being F to the n, and our edges being three uniform tuples from F to the n. And so we are looking at the ones that form arithmetic progressions, but they are distinct. So we say that the closure is this. So we're just throwing in the rest of the points that we were missing. And so in general, instead of codegrees here, we're going to be thinking about projections. So here we're looking at, so I'm thinking of this as a T-uniform hypergraph on ground set f to the n, and a non-empty subset of this. So we're going to define the projection to be the projection of h onto the set of coordinates. So here, we're going to take the x's where y is in h with yi equal to xi for all I in S. So in hypergraph terms that I'm more familiar with, we're thinking of these, we call them fiber hypergraphs or shadow graphs. And so you're looking at S-uniform hypergraphs consisting of the tuples that can be extended to the edges. So, before with our codegree conditions, we were really concerned about extending things to proper edges. So here, by formulating things in terms of projections, we can talk about the dimension of the projections, which is talking about how many edges live here. And so we can reformulate things in terms of the projections. So let's go back to our example and calculate some of these projections. So here we just get f to the n. Here we get the whole thing. And here we get x not equal to y, the tuples. So let's introduce a little bit more notation. So here we say that h is h independent, I is h independent if we cannot find x1 through xt in I, where this is a tuple in h. And we have a definition for being almost h independent. So if we contain something as a subset that has dimension equal to it but is h independent. So in particular, if you are h independent, you are also almost h independent. Okay, so I'll mention the full statement and then maybe I'll say some hand-wavy things. So we start out with an irreducible Zariski constructible set. And then this is what we're doing for our codegree conditions. So we construct partial fingerprints. So fundamentally, we are still doing a Scythe algorithm. I think it, in general, would be nice to have a non-algorithmic proof of these containers' results. But we are doing a Scythe algorithm constructing partial fingerprints and a container C, where the dimension of C is strictly less than n. And I will remark in practice, sometimes the dimension could be exactly n minus 1, but we could iterate this process and get something that's much smaller. So this is our containers type statement. And we use it to show a statement in algebraic geometry. So if we start out with an irreducible Zariski constructible set, so again, I'm thinking that these as algebraic T-uniform hypergraphs with the codegree conditions, then the image of a generic rational map of degree at least T minus 1 is not almost H independent. So I'm going to be a little bit hand-wavy here, but maybe try to explain in essence what we were trying to do. So if you take like a random algebraic set, so the natural question was, is it progression-free? Like, can you find arithmetic progressions or not? And so in general, we have a lot of structure. Like, there will be a lot of them, but in some senses, if you change the degrees of freedom, give more degrees of freedom, then things start acting a little bit more random. So thank you for your attention.
Are there any questions for Michelle?
Yeah, Peter.
So if you have a 1 plus little o of 1 factor in the exponent when you're talking about upper bounds on number of independent sets, right?
Right.
So do these techniques ever get you I'll actually plus big O of n in the exponent, like a constant?
So I will mention, so I was talking about some of my work using graph containers. Let me see if I can find this slide. So we were able to show this using graph containers, but we were trying to do things with t-intersecting families as well. So like graph and hypergraph containers did not hold in these cases, but we were able to get a better result than this. So, and I'd be happy to talk to you more about it later, but instead of using the graph containers, so we included it in the paper because I think, especially if you're interested in learning more about the technique, it is a nice exposition of how to apply containers. But instead we actually used set pair inequalities to try to do things more hands-on. And so we were able to get, for the t-intersecting, so t-intersecting means each of them intersect in at least t elements. So we're able to do a little bit better. So the answer is not really using graph containers, but with clever ideas, it actually was a very simple technique. You can sort of do better. And I'd be happy to like share with you the proof because it is very simple.
Any other questions? Okay, you use this to count our favorite new structures, the two polymatroids.
Okay, I have not, but that would definitely be a great question. In general, so like we were sort of interested in these algebraic geometric things in of themselves, but it would be nice if there were applications or if you could count things more directly than sort of moving them to hypergraphs and then trying to do stuff. But yeah, that definitely would be interesting.
Does it work for non-uniform hypergraphs?
So I believe if you do k-bounded, it should work. Don't quote me on that though. But yeah.
All right, any other questions? Otherwise, we'll continue at 11:20.